Welcome. In this video, I wanted to hopefully clear a mistake, potentially a confusion. A mistake which could lead to a confusion based on the exercise we did in class. So I wanted to do two methods to confirm our findings. Okay, so the problem that we had was that of a wavelength, which is, a photon with a certain wavelength, which is observed in a hydrogen spectrum. When an electron transitions from some initial energy orbit, from some electron orbit or shell, and then it lands on the fifth orbit. And then they ask us to find what the initial level must have been. What was the source level for this electron? It started off at this source and it ended up at this level, and the result was that we observed this wavelength. However, they don't specify to us what wavelength, or rather what spectrum this is. It could be an emission spectrum, it could be an absorption spectrum. Okay, so one method of approaching this problem is to use this formula, which was used for hydrogen before Niels Bohr's theory of the hydrogen atom. So you can use this equation. This equation was developed from purely experimental data. It's an empirical, basically, relationship between the the transitions between energy levels and the related wavelength. However, there is a condition to the use of this formula. This formula is applicable provided that this orbit here, or the quantum number of that orbit, must be always smaller than that. So by using this formula, or rather this formula already limits us to an emission spectrum. In other words, we must have started at an energy level which has a larger quantum orbit or quantum number than the final. So the point is, 5 is going to be less than whatever Ni is. So that's the only time this formula is applicable. The condition is that Nf must always be less than Ni. Okay, and if we're to use this formula, observing this condition here, eventually over here it's just mathematics and some numerics, and what I found was that the initial orbit from which the electron must have been should be labeled by quantum number 7. So you can check this out. I know in class, I believe we got 4, if I remember correctly. I think we found that it must have been, the electron must have initially been in level 4, but this formula actually shows us that we must have been dealing with an emission spectrum, not an absorption. Okay. Alrighty. Then the second method, which is similar to the method we use in class, and I'm going to highlight where things went south. Okay. So we know that the electron eventually lands on the 5th energy level, but we don't know where it starts. But what we do know is the difference between those two energy levels will give us a wavelength given by this, 4.653 micrometers. And we can find that energy that corresponds to that wavelength, and that specific energy is given by 0.266495 electron volt. Now, it is important to realize that when it comes to hydrogen, and you can review this in your notes, the delta E here is a bit of a misnomer, or a bit of a confusing. When we say delta here, we don't mean final minus initial. In the context of hydrogen, or typically with transitions, it has to do with initial and final. That's when you're emitting, because we know that the initial energy is going to be larger than the final when you are emitting a photon. when you are emitting a photon, the initial is always larger than the final. So when we say delta, we really mean the larger energy minus the lower energy. So I think that's where the mistake crept in class. I did not pay careful attention as to this difference. I simply just took it as final minus initial. And if you take final minus initial, you're going to get that number, the quantum number, being equal to 4, which is really not corresponding to the hydrogen spectrum. Okay, so now, having learned that the difference between these two energy levels is given by this, we can then substitute that delta E on the left to be that 0.026. Okay, I see I didn't do it directly here. But let's go here. Remember, the energy spectrum of a hydrogen atom is given by this. E sub n is equals to minus 13.6 over n squared. So when we're in the initial energy level, the energy corresponding to that energy level is going to be minus 13.6 divided by Ni squared. But the final one we know is 5. So we can substitute that in there. And if you clean this stuff up, you might realize that this formula is starting to take the similar form as this. You might see that 1 over nf squared minus 1 over Ni squared. And if you carefully take care of the algebra, I skipped some steps for the brevity of the slides and the video, but you can check that you will end up with this when you clean these numbers up. So delta E is going to be that value, and divided by 13.6, and subtract this from 1 over nf squared, and f is 5, so that's going to be 1 over 25, and you're going to end up with this value. And if you invert, you will find that the square of Ni is equal to 49, hence this tells us that Ni must be 7. I hope this helps clarify any confusion you might have. But if you still have any questions, please post them below on the chat. I will attend to them. Alrighty, see you in the next one.